In last lecture, we have discussed about state minimization and design of the sequential circuits. We have done an example to design a sequential circuit with the help of D flip-flop, and we are provided with the state diagram. Now, suppose consider another example. Given the state table, as the state table and the state diagram both are just equivalent, and the way of representation is just quite different. Both are the same thing. So in the last question we were given with the state diagram, and now in this example we are given with the state table. So given the state table, design the circuit using JK flip-flop. This is your table. You are given with present state, next state, and the input combination. So present states are notated with A and B. Here input is notated with X, and then next state is again A and B. As we have to design with the help of the JK flip-flop, and we are given with present state and the next state. So looking into the present state of A and the present state of B. So as here are only two states, 2 bits are required to represent the states. That means we need 2 flip-flops. Suppose the first flip-flop is JAKA and the next second flip-flop is JBKB. So with the help of the present state of A and the present state of B, we find the value of JA and KA with the help of the excitation table, where we are provided with the present state and the next state, and we have to find out the excitation inputs. So with the help of input A and B, we find out JAK, and with the help of present state and the next state B, we will find out the excitation input for JBKB. So these are the excitation inputs. The same we have done in when we are discussing or we are designing the counters, sequential counters. So what we do, we have to solve 4 K maps, one for JA, KA, JB and KB, and the input for the K map will be A, B and X. So we have to solve the Boolean equation for all 4 inputs of the flip-flops. Now in the next step, we have to solve with the help of the K map. So JA comes to be BX bar, KA is BX, JB is X, and KB is A XOR B NOR. That means A XOR B. So when we have the excitation input for the required flip-flop, now we have to draw the circuit. In the next step, we put 2 flip-flops A and B, and the output of flip-flop is A bar, B bar. We have an external input X, and the internal input of the flip-flops is JAKA and JBKB respectively. So this is the way when we are given a state diagram or a state table, then what we have to do, we have to find out the excitation inputs. With the help of the present state, next state, we have to solve the K map for all the excitation inputs and the output, if any, and we have to draw the circuit with the solved Boolean functions. Now the next topic for the unit 3. Now onwards, we are combining unit 3 and 4. Some topics will be covered from here onwards from unit 3, and some of the topic will be from unit 4. So the both unit will run parallel. Now we are going to discuss the asynchronous sequential circuits. As far as syllabus is concerned, a little bit question will be asked from the asynchronous circuit, but the process of minimization of flow chart and the state table is covered in this asynchronous sequential circuit topic. So let us first discuss what the asynchronous sequential circuits are and how they differ from the synchronous sequential circuit, and what are the advantages and the disadvantages. Then we'll move further for the designing process. Now let us first discuss synchronous versus asynchronous. The asynchronous sequential circuits internal state can change at any instant of time when there is a change in the input variable. No clock signal is required and have better performance but hard to design due to timing problems. So these are the definitions and advantages of the asynchronous circuits. However, they are difficult to design due to timing problems. As clear from the name asynchronous, the clock is not required for the asynchronous sequential circuit. Here you can see in the block diagram, we have n number of inputs, x1 up to xn, m number of outputs, z1 to zm. We have some feedback. There is some delay. Delay may be with the help of flip-flop. Delay may be wired, or it may be a delay due to the wire. So here are the input to the feedback, that is denoted by y1, capital Y to capital K. We have k excitation variables, that is the next state, and small y1 to small yk. These are the feedback which is fed back as input. This is no k secondary variable. These are the present states. So present states are represented with small y. Next state is represented by the capital Y. We have n number of inputs, we have m number of outputs, and there is no need of any flip-flop, or we can say the clock is not required. On the other hand, synchronous sequential circuits, they are synchronized by a periodic train of clock pulse, that is the master clock pulse, and much easier to design than that. That's why it is preferred design style. You can see we have a combinational circuit. We have flip-flops. Flip-flops are activated with the help of clock pulse. We have input and we have output, and all the flip-flops are synchronized with the help of a master clock. So in asynchronous circuits, no clock pulse is required. In synchronous sequential circuits, all the flip-flops are synchronized with the help of a master clock pulse. So these are the advantages and disadvantages of the synchronous and asynchronous sequential circuits. Now let's move to the topic why the asynchronous circuits are used. As we have discussed that it is hard to design. They are used when speed of the operation is important, response quickly without waiting for a clock pulse in case of the sequential synchronous circuits. Until unless there is no active clock, whatever is the input, output will not change. But in case of the asynchronous circuits, as we change the input, the output will respond accordingly without waiting for a clock pulse. Also used in small independent systems, only a few components are required. Used when the input signals may change independently of the internal clock. That's why they are asynchronous in nature. And also used in communication between two units that have their own independent clocks, must be done in an asynchronous fashion. So these are the applications of the asynchronous sequential circuits. Now some definitions of the asynchronous sequential circuits are, so this is your n number of inputs. This is the block diagram. We have some combinational circuit, combination logic, m number of outputs, k excitation variable, that is next state, and k secondary variable, that's the present state. Present state is denoted by small y. Next state is denoted by the capital Y, and there is delay. Delay may be with the help of flip-flops or latches, or it is just a wired delay, that is the propagation delay. So we have inputs and outputs. Delay elements, only a short-term memory, may not really exist due to original gate delay. We have secondary variables, that is the current state, denoted by small y. We have excitation variable, that is the next state, that is capital Y, and have some delay in response to input change. So so far we have not discussed about the delay in the combination logic, but each and every gate have some specific delay. That's why whenever present state and the input anyone changes, there will be change in the output and the excitation variable or the next state, but this will be due after some delay, and this delay is due to the gate delay. I'm sorry. Now, mode of operation of asynchronous sequential circuits. The steady state condition, You have studied the transition and the steady state condition when you were in say network and system or circuit system. So current states and the next states are same in a steady state condition. Difference between y and y, that is the secondary variable, and the excitation variable will cause a transition. If there is a change in any one of it, that is present state or the next state, there will be a different, this will cause a transition. Or until unless the present state and the next state are same, we say that the circuit is in a steady state condition. Now the fundamental mode, no simultaneous change of two or more variables. That means at any time, a single bit or single variable should change. What is the case of gray code? So if we say, if we have two present state y1 and y2, the only one variable, only one secondary variable should change, either y1 or y2, because of both tries to change. If we change y1 and y2 both simultaneously, there will be a race between race condition, and that should be avoided. So we say that the circuit is operating in the fundamental mode. That means there is no simultaneous change of two or more variables. Now again, the time between two input changes must be longer than the time it takes the circuit to a stable state, and the stable state is said to be when small y and the capital Y are same. So it is necessary that we should know what is the time delay to propagate an input change to the output, and we should change input variable or the input after that much circuit delay, because otherwise there will be an internal state and the circuit will be unstable. The input signals change one at a time and only when the circuit is in stable state condition. This is the fundamental mode of operation of a asynchronous sequential circuit that should be kept in mind when we are operating with asynchronous sequential circuits. Now let us come to the point of transition table. A transition table is useful to analyze an asynchronous sequential circuit and the sequential from the sequential circuit diagram. This is same as we have done this state table. The same is here is the transition table. The procedure to obtain a transition table: determine all feedback loops in the circuit, mark input yi, small y, and output capital Y of each feedback loop, derive the Boolean function for all capital Y's, that is the second next state, plot each Y function in a map and combine all maps into one table, circle all those values of capital Y in each square that are equal to value of small y in the same row. So these are the process how to obtain a transition table, and that will be much easier when we'll discuss with an example that how to obtain a transition table. Suppose this is the circuit. We have two feedback path, y1 and y2, and we have only one input, that is x. So what we do, we cut the feedback and we try to find out the equation for capital Y1 and capital Y2. So this comes to be x y1 x bar y2 and or. So x y1 or x bar y2, that is capital Y1. Similarly, we can find out the y2, and y2 comes to be x bar y2 or x y1 bar. This is the value of y2. So here we get the value of y1 is x y1 plus x bar y2, and y2 is x y1 bar plus x bar y2. So simply what we have to do, we have to just find out what are the feedbacks, and with the feedback at the output we put capital Y, and at the input we put small y. Small y is the present state, capital Y is your next state. Now what we do, we plot y1 and y2 in another map. So here is y1 is x y1 plus x bar y2, and y2 is x y1 bar plus x bar y2. So we plot, and keep in mind that the present state y1, y2 should be at the column side, and x, that is the all input, should be at the row side. So these are the x1, y1, y2 present state, and x is the input. Here is the input, all input x1, x2, x3, whatever it is, it should be kept on the top of the map, and the current state at the side of the map. So as we have two current states y1, y2, there are four possible combination. We have only one input, it is has two possible combinations. So putting the value, this value is 0, 0, 0, that is the capital Y1 is 0, capital Y2 is 0, and X is 0. We put the value 0 and 0 is 0, 1 and 0 is 0. So 0 or 0 is 0. So in this way, we can find out the different value, binary values for each possible combinations. Similarly, we plot Y2 in the same way and put the value of y1, y2 and x. We get the map for y1 and map for y2, and we combine both y1 and y2. The first, this is y1, the y2, so y0, 0, next is 0, 1, here is 0, 1, next is 1, 1, 1, 1, 0, 1, so here is 0, 1, 1 and 1, 1, 1, 1 and 0, 1, 0, 0 and 0, here is 0, 0, 1 and 0, 1, 0. So in each row, whatever is the value, if the same, this capital Y, small y1 and y2 is equals to small y, and this is inside is your capital Y, the capital Y1 and capital Y2 combinedly is known as capital Y. Whenever Y equals to Y, circle the state. So here is 0, 0, so whatever, wherever is 0, 0, that should be circled. The 0, 1, here is 0, 1, that is circled. 1, 1, again 1, 1 is circled. 1, 0, 1, 0 is circled. So whatever is the circled state, that is known as stable state. So this capital Y is Y1 and Y2. You say 1, 0 in the same row is 1, 0, so then circle it, and it is known as stable state. So whichever state is circled in a row, that is known as stable state. So the transition table tells us about how the transition takes place when we change the input variable or the secondary variable, and whichever will be the stable state. A circle will be in the stable state, that means small y is equals to capital Y. Now the state table. This was your transition table. In the last example, we have found out in the last slide. So when input x changes from 0 to 1, while y equals to 0, 0, the y equals to 0, 0, and x is 0 initially, when input changes from 0 to 1. So what will happen when input changes from 0 to 1? It will move from 0, 0 to 0, 1. So what happens? Y changes to 0, 1, and which is a unstable state. You can see that this 0, 1 is not an unstable, this is an unstable state as it is not circled. So what happens? Y become now, whenever capital Y is 0, 1, after some time, this small y again becomes 0, 1. So y becomes 0, 1 after a short delay, and it is stable in the second row. The system comes here and it comes to be in the second row. In the second row, 0, 1 is a stable state. So in the next state is y equals to 0, 1. It moves like here. So each row must have at least one stable state in each and analyze each state in this way can obtain its state table. So this is the way how the state transition table is analyzed. So here is a present state and next state table. Now both are same. The representation of the present state next state table in a transition table. This is the difference. Only the way of representation is different. Transition table is represented in the map, and present state next state table is represented as a table. So here the total stable state is known as y1, y2 and x. So we can say whichever is circled, there are 4 total stable states And the first total stable state is 0, 0, 0. Next state is 0, 1 and 1, 0, 1, 1, 1, 1, 0 and 1, 0, 1. So these are the four stable state. So looking into a transition table, we can find out what are the total stable states, and just looking into the circles, we can find out that these states are total internal stable states. The flow table, similar to a transition table, flow table is just similar to the transition table, except that states are represented by letter symbols instead of the binary value. So suppose this is a state flow table. Here we have represented states by 0 and 1. So instead of 0, 1, we have represented as A, B, C, D. In the last state, if this table, I represent 0, 0 as A, 0, 1 as B, 1, 1 as C, and 1, 0 as D. So I have done the same here. 0, 0, 0, 1, 1, 1 and 1, 0. So it is equals to A equals to 0, 0, B equals to 0, 1, C equals to 1, 1 and D equals to 1, 0. Can also include the output variables. So when we are including the output variable, it is like this. This is another table which have two state with two internal state and two input and one output. So here x1 and x2 are two inputs. They are put aside. Y is only one, so it has two values A and B. So A comma 0, 0, A comma 1, B comma 1, these comma, the values after comma is the output value, and the circled value is your stable state. The suitable to obtain the logic diagram from it. So when we have a transition table, we can directly draw the circuit diagram with the help of the transition table. The primitive flow table, if only one stable state in each row, if in a table, if in a transition table, there is only one stable state. Here we can see here are three stable state. Here in each row, there is only one stable state, then it is said to be a primitive flow table. Now, suppose we are given a flow table and we have to draw the circuit with the help of the flow table, and our procedure is as followed. Assign to each state a distinct binary value, and this process is conversion of a flow table into a transition table, and obtain map for each secondary variable and the output. Now suppose this is our flow table. We have to draw the circuit for this particular flow table. A, B, these are the two values. So what we do, we assign A equals to 1 and B equals to A equals to 0 and B equals to 1. So we have plotted A equals to 0 and B equals to 1. And when we solve it with the help of the K map, Y equals to x1 x2 bar plus x1 y. So these are the two pairs. Similarly, we can plot the value of y. Y equals to this 0, 0, 0, 0, 0, 0, 1, 0. We have only single one, no pairing. So z equals to x1 x2 y. So we have the expression for next state and the output, and we can draw the circuit like this. Is the logic diagram which is obtained from the flow table. So the process is, whenever a flow table is given to you, just assign a binary value to the flow table, then it will be converted into a transition table, separate it out all secondary variables and outputs, draw the K map, solve the K map, and draw the circuit. So let us stop today's lecture here.